Swayam Prabha. Digital India. Educated India.
And welcome back to this lecture series on foundations of cyber physical systems. So in the last lecture we talked about due to the delay in the control update, how the augmented system analysis had to be created, and the controller has to be designed corresponding to that augmented system, right? So we'll just go a bit more deeper into what is the effect of such delay on stability and performance of control systems. So if you remember, the discussion we had was that the sensor to actuator delay was not trivial, but it was some significant value, but although also it was always getting computed below, within the deadline. So let's say this is where your this is your TK, that means the sampling happens at the kth point, and here the sampling will happen at the k plus 1th point. So with the kth measurements, the control task computation is going to happen. So this is the measurement happening here, and then the control task, let's say it executes here, and then again somehow it's getting preempted here, and then it is getting computed here, but it finishes here. The point is we are given a fixed delay. This was the constant delay model, where the delay is basically governed by some value which may be less than or equal to the triggering offset. That means this is where the update of the control action will happen, and then with the updated control action, that means UTK, you will be the system will evolve for this part, and before this the system's evolution up to this is happening with the previous control action. And just for your idea, these are the standard task notations we have been using. TM is the measurement task, TC is the control task, and then we have the actuation task which will be executing here, so that the actuation update is really computed before the triggering offset. So we are assuming that the triggering is happening here. That means here you have UK available. Just repeating a correction here. So this is where you have UK minus 1, right? And then we assume the constant delay model. We model the delay to be constant, and this should be less than or equal to the triggering time. So in a nice case, we can actually have this right here also. So we are assuming that the task will be triggered eventually here. That means the actuator will get start using the updated control input right here, and that's why we set the delay somewhere before that, so that the actuation task executes before that and the value is available, and then when the actuator is going to actually use the value, that is the point which is here, right? So that up to this, so you have UK minus 1 being used. Here UK has been computed, but this using this less than equal to, we can say that but it is still not used, and it will be used here when the triggering actually happens and the actuator actually gets that value. So please don't mind the scale of this picture. It may be quite possible that this entire dimension starting from here up to here, this interval is small, and really this interval is much bigger. Okay, so this is just for illustration here. So the point is, the control task will execute, then the actuation task will execute, and this entire thing should happen within this delay. So the actuation task will finish right here. That means once the actuation task finishes, the UK update is already there, but the triggering, that means the actuator using the actual value may start with a mild offset here. Okay, so from here the UK's value is going to be used for the rest of the period. Now the question that comes is, what about the other scenario, that is your sensor to actuation delay that we finally suffer that is greater than this deadline. So that means the actuator is supposed to sample the updated control right at this point, right, where the triggering will happen, right. So the actuator is supposed to sample the updated control, but that's not really available, because let's say due to delay in the control task or the actuation task, the final update on the control happens here, which is beyond the triggering of the actual of the actuator, right. So that means in this case the entire control command updation task is missing its deadline. So I mean, it can happen in a various possible ways, that it has been preempted too many times and then it was delayed, and then the actuation task, and the actuation task also need to happen within the deadline. So all these things could not be completed, and before that the actuator actually tried to sample the update if there is any on the control task with this offset. So just recalling from our previous picture, so this is what we had, like here is a measurement, then there is a task actuation, right, happening here, then again measurement actuation happening here. It is supposed to be like this, right, and this delay is kept something below the triggering interval, but somehow if this delay goes beyond that interval, then what situation will happen, that is what we are talking about here. So let's understand. So this is where the actuator is trying to sample if there is any update on the control, but the overall sense to actuation delay in this case, due to task preemption or extra computation or data communication delay, etc., between the actuator and the controller, or the controller and the bus, there were some delays, due to which this computation got delayed and it was completed beyond this triggering offset. That simply means that, well, the actuator is unable to get this update, right. So what happens in this scenario? The actuator needs to continue with the older control update only, right. So you need to have some strategies, like what to do here. So one strategy is that you kill the control task that is going to miss the deadline. So that means the control task execution is here, right, and it's still not finishing, and the actuator is expecting the update to be here, but the update is still not computed. So right here, when the system observes that there is no update, it can kill the control task execution, right, at that point, and it can just continue with the older value, okay. And there is also another strategy which is called delayed control, that, well, you can actually delay the actuation itself, but that will depend on the physics, that means how the system is really implemented, whether the actuator is actually allowed to delay updating the control from the task, right. So in very simple systems, what happens is that, well, the actuator simply doesn't wait, because it will be working with a fixed period h, and it will be working with this offset tr. So every time at a fixed period, it is going to sample and figure out whether there is any control update or not, and in that case, if there is no update, it will simply continue with the older control update, okay, and the current control task execution will simply be dropped. So that's a kill job strategy. So the strategy to be chosen, it will depend on the performance of the system, well, how good the control loop is performing with respect to its current sampling and plant model, stability requirement, etc., and also what is the amount of processor utilization that is there. So as an example, let's consider a situation. We will see that, well, how this kill job strategy can kind of affect the control task execution. So suppose you have two control tasks, T1 and T2, running on a single processor with these periodicities as given. So T1 has 0.4, T2 has something 0.6, so T1 will have a higher priority, and let's say there is also an authentication task which will always be running with a much smaller periodicity, and it will be running with periodicity 0.3, and it is trying to secure the system, it's basically monitoring the values, etc., right. And since this has a very smaller priority, it will run much frequently. Now let's consider that we are looking for an RM scheduling, okay. So that would mean that this priorities will be in the order of frequency of the tasks. That means the smaller the periodicity, the higher the priority, though this will be the priority order. Security task will have the highest priority, then you have control task 1's priority, then you have control task 2's priority. So observe that this task set won't be RM schedulable. So also just to understand why it won't be, let's look at the schedule here. Okay. So this is the table we had here. So we are just reproducing here, and based on an RM strategy we are trying to build the schedule. Okay. So you see that 3 has the highest priority. So 3's first instance will go in here. So when I write T31, it means task 3's first instance. Okay. It is something like a notation we used earlier, which is this. Okay. But here we are writing with a comma. That's fine. So after this finishes, we will have T1 because that has the second priority, and then we will have T2 which has the third priority, and then T3 has an instance which will arrive right here because it has a period of 0.3. Deadline is same as period in this case. So that's why it will preempt T21, and then T3's second instance will execute here, right, and it will take 0.05 unit of time. So the time will progress from 0.3 to 0.35, and then T21's pending instance which was preempted, it will start, and T21 in total is going to take 0.6 execution time, and as you can see that it will complete here. It will still execute here, but then it won't really complete, right, because it needs 0.6, and here you have a 0.1 done, here you have a 0.05 done, so not really completing, right. So in this time T1's second instance will arrive. So T1's second instance will now fully occupy the CPU for 0.25 seconds. Okay. So it will end somewhere. So T1 second instance starts here, and it is going to take 0.15 seconds, and so it starts at 0.4 and it will end at 0.55. Okay. So then again T2 second instance can start, right, and now T2's second instance will take this much amount of time, and T2's second instance will finish, right. But if you see for T2 it will have its when is it supposed to come again? Here its period and deadline are both 0.6, right. So here T2's second instance, here T2's second instance is coming, and 3's third instance is coming, right. But could T2's first instance finish? Let's calculate the execution time. Here it was 0.1. So in total we have 0.2 of the job done, but in total it needed 0.6, right. So it doesn't finish. So that means before it finishes it will again be preempted, and by now the deadline is also over, right. So then T2's first instance is going to miss the deadline right here, right. So fine, then T2's second instance has come and T3's third instance has come, right. So let's say third instance will have a higher priority, and we will execute it right here, and then we will continue with T2's second instance. So first instance has already missed its deadline, no point in continuing with it, right. So T2's second instance continues here, and then T1's first instance is going to come. So if you see here T2's first instance, I could execute only 0.2 seconds, but we in total required this, so that was not satisfied, right. So it missed its deadline. So T3's third instance has arrived, it will execute, and then T2's second instance will execute because T1 second instance is yet to arrive. So T2's second instance here it will execute for 0.15 seconds, and at the end of it T1's third instance arrived, right? So T1's third instance has arrived, so T2 will again be preempted. It needs another 0.1 second, right? So it will be preempted. So T1's third instance will execute here, and then again T3 will come, T3 will occupy the CPU for some small amount of time, and then again T1 third instance will occupy the CPU, and it will end here, right? So once it ends, T2 second instance will again restart, and whatever 0.2 second was left, it will continue, it will complete right here. Okay. So if you see in this period, we have actually drawn this thing up to the hyper period of these three tasks. So that's the hyper period of the task. So we have drawn it up to 1.2, and because we understand that if we can schedule these tasks up to the hyper period, then the tasks will be infinitely schedulable for any number of periodic actuations. The tasks will be schedulable, right? So if we see that inside this hyper period, whatever has been the instances of T1 and T3, the tasks with the higher priorities, they could all be scheduled, but T2's first instance could not be scheduled. Now what does this really mean? That means that, well, you understand that this pattern will continue, like who will be schedulable, who will be not schedulable. This will continue in all the consecutive hyper periods, right? So this means for the task T1, I had how many instances? So inside the hyper period, so I had 3 instances. So T1 arrived here, here, and here. All were schedulable. So I can write a deadline hit miss pattern for T1 like this. A deadline hit, that means the deadline being satisfied, is denoted by a 1, and the deadline being missed, that means the deadline overrun, the execution overrun the deadline is denoted by 0. So then the hit miss pattern for T1 would be this, right? Now similarly for T2, how many instances are there? 1.2 is the hyper period, 0.6 is the execution time, so that's 2, right? So T2 we had one instance here, and we had another instance here. Now as we saw from our analysis, T2 missed its first deadline, and then it met its second deadline. So for T2 the hit miss pattern is 0, 1, right? And then for T3, how many instances were there? For T3 I had this as well as this, and if we do the hyper period analysis, total hyper period 1.2, the period of T3 is this, so I will indeed have 4 instances, and all were being executed, right? So the pattern is 1 to the power 4. So I can write the patterns are 1 cube, that is 3 ones, the pattern is 0, 1, and the pattern is 1 to the power 4 for T1, T2, and T3. What is the importance of these patterns? Let's understand that when this task will execute by RM on the processor, under the strategy that whenever a task misses its deadline, it is immediately killed, right? And because that's what we did. We didn't allow T21 to continue beyond its deadline, although it had some remaining execution. So under that, we can actually derive this kind of patterns, and we can say that, well, over the hyper period, these are the ways in which the task will execute, and they will hit and miss following this pattern forever. So for T1, if I continue in RM, T1 will always meet the sensor to actuation delay, or the period that has been assigned to it corresponding to the delay. Sorry, and not the sensor actuation delay, but the period that has been assigned to it. And also for T2, I can say that, well, this task doesn't really work, because it will always miss its first instance, and it will actually satisfy its second instance. So that's how we are showing it. Now note one thing: when we are doing this analysis, we are actually ignoring certain things, right? Because we are only considering that the control task's execution can be preempted by other control tasks and security tasks. After that, there may be an actuation task, there may be delays. We are ignoring those things. So we are simply saying that, well, if the control task executes within this time, then it will satisfy whatever is the delay it is supposed to be designed with, right? And if the control task doesn't meet its deadline here on the CPU, then fine, then that means after this deadline immediately there must have been a task triggering, so it has missed that task triggering also. So this is a simplistic method. We can actually create problems with much more detailed models, and that we will see while doing our tutorials and stuff. So here for the time being, let's go on with this simplistic model. We are just assuming that if the control task is dropped, that means it misses the deadline. That means for the corresponding control action, there has been a deadline overrun, and this control task instance has been killed, and the control update didn't happen. So UK works with UK -1. So that's how simplistically we are continuing here. But I'll just repeat what we really mean here. I mean, what would have actually happened in the architecture would have been this: that well, this task missed its deadline, and due to that we didn't allow it to continue. The reason is that well, even if it continued, it will finish at a later time, and then there would be an actuation task which is going to take this input and then write the value in the actuator, and then whatever time that will take, before that the actuator's triggering will happen. So that's what we are assuming here, that this deadline is sacrosanct. If this deadline is missed, then immediately as a consequent event, the actuator triggering will not get this control task update, and hence we must kill the control task whenever it misses the deadline on the processor. So that's how we are modeling it here. So if we continue like this, now the question is, well, what to do about it, right? So let's try to see that what can be done. For example, we see that since the tasks are not RM schedulable, one possible solution would be that well, we drop this T2's execution. Okay, so we drop this T2's first instance execution, or do something about it. Okay, so if you see that, then if we really see in our analysis, like we saw that well, this T12 has missed its deadline, so that means well, there was no point in giving it the CPU at all, right? Because eventually it got killed in this way, right? And now see that what can be other situations. The other situations can be, let's say like this. Suppose I do not want this to happen, that this task 2 should not miss the deadline. Okay, but then we have to do something about it, right? If I don't want task 2 to miss the deadline, then I should be, the only thing maybe that I can do is I should drop some other instance of some other task actuation. Now the question is, why should I do that? Okay, the idea is that well, it can be done. It depends on what are the control tasks and which control loops they are controlling. So typically when somebody is designing a controller and implementing it, people usually over budget. That means let's say you have a plant which you are sampling pretty fast, and due to that fast sampling you have got the corresponding control tasks which are also executing very frequently. So that means whatever would have been the minimum required sampling period, so that the corresponding controller stabilizes that loop, you may have chosen a much higher period with respect to that, and that is why your task is executing more frequently. So that's like a robustness of the loop, right? Now the thing is that since by design the controller has some robustness, it may not matter if that some instances of the controller are missed, right? So depending on that, suppose I have a set of control tasks which I am co-scheduling, I can go and check that well, which are the tasks which are more robust. That means if I can eliminate one or two instances of those tasks here and there, it doesn't really matter for the corresponding controller. Okay. Now this is also a control theoretic problem, so for which the real-time platform designer has to take the feedback from the control engineer and understand that, well, you see, for this task it is not that much, the plant may be not that much sensitive to the controller actions because it's not a very fast control loop. Okay. So for that control loop, maybe if you drop some instances, it may be okay, right? So depending on that, such decisions can be taken. Here we are just showing it from a scheduling perspective. So we are just telling that, suppose the previous solution that we had, that, well, I just go by RM scheduling, since the tasks are not actually RM schedulable. So what happens is, over the period, this task T2 is missing its first deadline for the first instance. So that means T2 will execute with, let's say, 50% of control actions really happening and 50% getting dropped. But let's say T2 is controlling a plant for which this much amount of drops is not allowable, right? The control engineer tells you by some analysis that this is not allowable. Then what to do? Let's look for some other task. Let's say for T1, I get the feedback that, well, for T1, if you drop 33% or some kind of something like that, that many control actuations, it is fine, right? So then let's see that, well, can I intentionally drop certain instances of T1? What does it mean by dropping the instance of T1? That means I do not go by simple periodic scheduling. Instead of dispatching all instances of the task, I dispatch as per this kind of patterns. So what I do is, for T1, I figure out that, well, maybe giving 30% or 40% drops, that means not giving the control updates, is fine, because the plant can withstand that and still give me the required performance. So I will nicely try to choose that, well, these are the instances of T1 that I can drop, and those empty slots of the processor I can give to T2, so that T2 can execute with all its instances. So let's suppose we decide something like this. Okay. And now let's see that how the execution happens. So suppose I decide that, well, I will drop the second instance of T1, T12 in every hyper period. Okay. And now it's not that I am running T1 and it is going to miss its deadline, right? So that's not going to happen, because it's an RM strategy. What I will do is, when I will dispatch all these tasks T1, T2 and T3, I will not dispatch all its instances. I will judiciously choose and dispatch following this kind of pre-designed hit miss patterns, that or let's call them task execution patterns. So again I will repeat, I do not do periodic scheduling. That means I do not really dispatch all the tasks, all instances, that means all the jobs corresponding to each task with the desired periodicity, but I really dispatch them following these patterns. So that means I will dispatch T2's first instance at 0 offset, I will dispatch T2's second instance at 0.6 offset, 0.6 seconds, right, inside this hyper period. And then again at 1.2, when the first hyper period ends and the next one starts, I will again dispatch T2's instance, etc. And for T1, I will dispatch the first instance. We are assuming here there are no offsets, but there can be offsets, fine, as per the scheduling. Then I do not dispatch the second instance at this 0.4, okay. But then again I dispatch the third instance at 0.8. So that's how I do it here. Okay. So let's see that if I do that, well, I am giving T1's first instance here. I do not give T1's second instance here. I give T1's third instance here. I dispatch T2's first instance here, and I dispatch T2's second instance here, and I dispatch T3's all 4 instances at these positions. Now let's schedule them. So here T3 will execute highest priority, then T1's first instance executes, then T2's first instance executes as per the priority, because the RM doesn't know, right, that what we are dispatching or not. Whatever you are dispatching, based on that RM is deciding based on the priorities, right? And then T2's second instance and then T2's first instance will continue here, and here you see there is a nice blank spot because now I have not dispatched T1, so T1 is not causing any contention here, okay. T1 is not causing any contention to T21, so T21 doesn't need to drop here and T21 can continue up to this. So here T21 has executed for 0.1 second, and here T21 could execute for 0.15 second, and T21 completes its execution of 0.25, so it finishes here, right. Again here T2's second instance will come, T3's third instance will come, which will execute, then second instance starts. Now T1's instance will come, it will execute, T3's fourth instance will preempt it, T1's third instance will resume and finish, and then T2's second instance will resume and finish. So all good. Only what we did is to make this task as schedulable, we took a judicious decision that, well, I will intentionally drop T1's second instance so that things work. Now it need not be the only solution, there could have been another solution also. I mean, you can actually figure out which are the solutions by doing schedulability tests. So suppose instead of dropping the second, you could have also dropped T1's first instance, so that the pattern is this, right. So then what will happen is you drop T1's first instance, that will also have an effect that, well, then you don't have arrival of T1 here, you have arrivals of T2 and T3. T3 will execute, then immediately T2 will get the CPU and it will execute for its desired time. Then T3's second instance will come, and then T1's second instance, which you have not dropped, will come and it will occupy the CPU. So you see that here again all these tasks are schedulable with T1's just first instance drop. So these are important design decisions. Now what is the advantage of this kind of aperiodic scheduling? The advantage is that you don't need to reduce the control loop's periodicity, because if you reduce the control loop's periodicity, then you are practically dropping more instances of actuation, update and sampling you could have done. So you are doing a fine-grained scheduling of the controllers, and you are judiciously choosing which instances of the task to drop, and at the same time you are not kind of reducing the period that we do typically in periodic scheduling of control loops, okay. So this is one possible technique that people have used, and you have found that, well, with respect to schedulability this is fine. So you can choose what should be a hit miss pattern, and because in case tasks are not schedulable, you can choose which of the tasks to actually drop. So you know that this will not finish, so either you drop that instance, or if you see that, well, this task instance for this control loop must execute, so in order to execute it, you have to avoid interference from higher priority tasks, and if the control loops corresponding to those higher priority tasks are robust and some of their executions can be skipped, then you intentionally skip one or two of those executions, as we see in these examples, and you decide that, well, instead of doing full periodic control, I will do aperiodic pattern based control. I will give the patterns and say that, well, inside your hyper period you need not execute all the tasks that arrive, you actually execute some of them following this kind of patterns. So that's the learning from this discussion here. Now here we have a very important question: can we just choose and skip anything? Because then you see the control engineer will be very angry with you that, well, you cannot really do that. I mean, there is a mathematical guarantee to be maintained, etc., etc. So you cannot ad hocly decide that, well, I will skip this or this. There has to be a mathematical rigorous guarantee for that, right? So the number of skips is typically bounded by an upper limit. So let's say you model this as a switched control system. So whenever the switch is closed, the control input is computed and transmitted to the plant. When the switch is open, that means the control input is neither computed and not transmitted to the plant. That means the plant will simply continue with its older control input that was there. Let's say this switching rate is R. So R is a rate, that means 1 minus R is what we call as the drop rate. That means let's say there are 100 consecutive iterations. R is the execution rate, let that be 0.9. So then drop rate is 0.1. So that means you are saying that, well, out of every 100 consecutive control actions on the plant, let's say 10 of them will be dropped. Now the question is, there exists rigorous theory which says that, well, what is the upper bound of these drop rates, or what is the lower bound of these execution rates? Okay, that minimum number of times you must execute, so that, by the way, note that this is a rate, this is not a value. Okay, that means if you have the rate as R, then that means that out of n consecutive cycles of execution, this n times R number of cycles, the control must really be updated. Okay, so R is basically a value between 0 and 1 here. So there are several theorems on this in control theory literature. We will just show one of the simpler and popular ones. So this is Branicki's based on Branicki's paper on around this time. The reference is here. So what it says is that, suppose you have the closed loop, and the closed loop is stable without any kind of this kind of drops that are happening, and for the closed loop you have the plant's model as phi and gamma, and the controller is k, and so the closed loop is given by phi minus gamma k. This is on the discrete domain. In the discrete domain, we can say that, well, this matrix is Cart, that means it is Cart stable. That means all the eigenvalues of this closed loop of this system matrix in the closed loop are within the unit circle. Okay, so when do I say, what does the theorem state? The theorem states that if the open loop system, that means the system without the control, is marginally stable, then the system is exponentially stable for all switchings, all execution rates. What does it mean? Suppose even without the control, the system is marginally stable. That means what? That means you need not really compute and execute. You don't really care, right? Because, well, whatever is your control execution rate, you are always able to meet the deadline of the control task, or you are not able to meet it that frequently, doesn't matter. The system will be exponentially stable. That's what the theorem says. And then that now comes the other tricky part, that suppose in open loop the system is unstable, because that's the most common case, right? That's why you will design the controller, or you will design the controller to have higher performance for a system which is maybe open loop stable but not performing well, right? So in the second case, when your open loop is unstable, then but the additional condition is, well, in open loop it is unstable, but after closing the loop, your phi minus gamma k is actually stable. That means the closed loop is stable. Then under what drop rate the system will still remain exponentially stable is given by this bound. That means R, of course, it is less than equal to 1, but R must be greater than this factor, where this factor has two parameters, gamma 1 and gamma 2, and gamma 1 is parameterized with the eigenvalue of the closed loop, and similarly gamma 2 is also parameterized with the maximum eigenvalue of the closed loop. Okay. So what this theorem does is, we are not going into the details and how this theorem can be proved. Those things are there nicely in these papers. So what you can do is you can use the closed loop parameters to figure out, using this theorem, that what should be the minimum rate at which the switch must close. That means out of n number of executions, how many of those executions must meet the deadline. That means I also know that how many of those executions can be actually skipped in case I have to accommodate other tasks while scheduling them. So that's the learning we wanted to impart from this theorem. Okay. So just one example. So suppose you have our old favorite trajectory control system. System states the deviation from trajectory and velocity. The output is the deviation and the control input is the acceleration. Okay. So for this the open loop lambda max is 1. So that means the system is marginally stable in the open loop. So the closed loop system is stable I mean with any execution rate, okay, even if the loop doesn't close. So that may, if you now see the plot, you will see that, well, the output is I mean you have three plots here with 50% skip on the control input here, and you have 75% skip on the control input, and you also have no skip. That means this is the proper suitable periodic situation. You see that in all cases you are kind of stabilizing, right, because the system by nature is open loop stable, because the maximum eigenvalue just considering phi is 1. That means all the other eigenvalues are within the unit circle, so it's a marginally stable system. So whatever, how many drops you give here doesn't matter, the system's output is stable. But now let's take a system with a set of different parameters, okay. So when you take the system with a set of different parameters, it is an unstable open loop. For this system matrix, you see that the lambda max is greater than 1. So here you can see that, well, you can actually design the R based on these maximum eigenvalues of the open loop and the closed loop, and in this case this thing will evaluate to 0.5. So that means the minimum rate that you need to maintain is you need to actually complete half of those control executions. So you see this really comes out nicely. So the green curve is for perfect periodic control. The blue curve is actually saying that, well, if your execution rate is at least 50%, that means at least half of the control executions you are really completing without missing the task deadlines. So you see that the system response is not as nice as the periodic case, right? But still, so that means there will be jerks in the ACC, the vehicle's movement, but eventually the vehicle will kind of hover around the target speed, right? There will be disturbances, there will be jerks, but it will hover around, not smoothly, but it will, right? So it will not be unstable. But see, the moment the rate goes below 50%, that means you are not closing the loop fast enough, you are missing too many control updates, it's completely unstable. So that's the knowledge we wanted to impart using a real example here. So I hope with this you have got enough idea about how performance and scheduling. So this is a very important point. We spend a lot of time here. The reason is this is really what we should mean by cyber physical systems. You have knowledge from embedded and real-time systems and scheduling and timing analysis. You have knowledge from control theory, and you will like to apply them together to design the final implementation. So that's really how CPS systems need to be studied and designed. Okay. Thank you for your attention. We will end this module here.